Kia ora tātou, ko Andrew Sargent toka wingua. I'm here to introduce Dilution Holmes. She's a Kaiako Mātua of Chemistry at Te Kora, the same place I work. And I'll hand it over to you, Dilution.
Kia ora. As Andrew said, my name's Dilution Holmes, ko Dilution Holmes toka ingoa, and I will be going over the Aqueous tonight. So it's a gorgeous day in Wellington, so sorry for taking you away from that, but hopefully you will learn something. So I'll just quickly share my screen. And hopefully you can see the 91392, which we're going to be going over, which is about the equilibrium principles in aqueous systems, which is 5 credits. Now, the first thing you should always be looking at is what help is available. And of course, the biggest help is the resource booklet. So make sure that you look at the resource booklet that comes with the exam. It's normally a separate booklet. Make sure you use it, because as you can see, a lot of equations are given, and very big plus that's only come in recently from last year, they give you all the complex ions. So you can check very carefully, and they've introduced some new ones as well, like nickel cyanide, and nickel with ammonia. So you can check to see that your formulae are correct. You don't have to learn it off by heart. It's nice though, instead of referring back to the resource booklet all the time while you're just checking over the exam, is I remember this as Zinc, Zinc N, Zelpo, and niacin. So if you're looking for baby names for future or band names, you can try one of those. So Zinc, I hope you realize, is zinc, and nickel, the A for silver, then Ni for nickel, and then the C for copper. So those all form complex ions with ammonia. Zelp would be zinc, aluminium, Al, and then L and P is for lead, because the symbol is really Pb, and that's for OH. And then for niacin is the complex ions formed with cyanide, and so it's nickel and silver. So just sort of memory help, because if you're trying to do all 3 exams, it's a lot to get through. So let's have a look now at what you need to know. So that's quite a bit there, but pretty much, although this is not really in the standard, you need to know, and I find a lot of students struggle with this, is when you get given a compound, you don't know what to do with it, and then your equations are wrong, and so on. So we're going to spend a little bit of time with that, and then we'll go into this. This is an achieved level, but you need to get it right to do any better for the merit and excellence. And this goes to achieved merit level, and that's sort of over there. Then we start getting to more the excellence, the merit and excellence sort of questions. So those tend to be all the ones under solubility. Then you need to know about strong and weak acids. So these you are given in the assessment specifications. They expect you to know these. So if you do not know them, or you didn't realize you had to know them off by heart, then spend this weekend before Tuesday learning them. So if they give you HCl, HBr, HNO3, or sulfuric acid, they would expect you to know that those are strong acids. If in the paper they give you HF or ethanoic acid or ammonium, then they expect you to know it's a weak acid. Similarly for strong bases, potassium and sodium hydroxides, and for weak bases, ammonia, methylamine, and then the ethanoate ion. So please make sure you know those. Then how would you use those? You would use these in hydrolysis equations, working out what species are in solution and ordering them from highest to lowest or lowest to highest. Then the properties of solutions, so that would be the conductivity and perhaps the pH. And then to be able to do this, you also have to do some calculations, and from those you need to be able to write Ka and Kb expressions. So those are what we're going to be going through tonight. Then finally, you've got titrations, so where we use strong acids and weak acids, strong bases and weak bases when we titrate them. So there are 3 types of titration graphs you need to be able to recognize or perhaps even draw. Sometimes they make you draw parts of the titration curve. And so it could be a strong acid, strong base. I have never seen that one come up in the exam simply because that's the easiest one, but you never know, it could come up. Otherwise, it's the strong acid, weak base, or the strong base, weak acid. And you could be starting either from a low pH with the acid, or you could be starting from a high pH, which is if you're starting with the base. Then round with the titration curves, you not only do those pH calculations, so that sort of links over here, you might have to discuss buffer regions and buffer calculations, and also what would be a suitable indicator to use for any one of these 3 titrations. So that's a quick overview. Let's have now a look at each of these points. So please pop in questions in the chat if you need to, or if I'm going too fast and you want me to go over a point in a little bit more detail. So this is the first part. I found a big stumbling block is being able to look at a compound and then work out how does it split, what ions. So the first thing you need to know is, of course, you're given a periodic table, and if you sort of do more or less down over here, these are the non-metals and these are the metals. So if you've got an ionic substance, it's always a metal with a non-metal. So all what I've listed here are from the last 5-6 exam papers from 2000, well, it's from about 2013. These are all the ones that have come up in past exam papers. The only one that hasn't is this one, but I thought, who knows, they could bring that in. So let's have a look at these. If you don't know your charges, because they don't give you the charges as such, you can use a periodic table for simple ions. So, for instance, Br is in group 17 over here. I'm just going to tidy this up a little bit because otherwise it gets rather complicated. So everything in group 17 has got a valency, and therefore if it becomes an ion, a charge, it will have a valency of 1 and therefore a charge of -1. For an ion that's formed from an element in group 2, it'll be -2. Everything in group 1 will have a charge of +1. Everything in group 2 will have a charge of +2. And in group 13 +3, but you don't really go sort of aluminium's the last one. Lead is a little bit of a tricky one because it is in group 14. And the ones at the top here, well, they don't form ions because they're non-metals. That's a metalloid. But lead can form either the 2+ ion or the 4+ ion. The +2 is more common, but you can use the information from what it's combined with. So if you've got PbBr2, well, let me just. So if I've got Pb and it's combined, no, remember this is not a molecule, I'm just trying to show it. If each of these is a negative charge, because Br is sitting in group 17, then it means that the Pb must be a +2 charge to cancel out the charges on the 2 Brs. So have a look, use the periodic table if you don't know your ions. If you've got complex ions or polyatomic ions like carbonate or hydroxide, you just got to have to learn them. One way is, I've got this mnemonic if you want to learn how many oxygens are in a polyatomic ion and the charge. This only applies for 8 compounds, so sulfate, chlorate, carbonate, nitrate, phosphate. And so as a mnemonic, you can think of school chef cooks next pancake. And what we do here is the vowels give the, if I just do it as a highlighter, the vowels give the charge. So you'll see it's 2 minus. That's got only one vowel, so it's 1 negative, 2 vowels, 2 negative, 1 vowel, 1 negative, and this has got 3. Sorry, I've overlapped there, but you get the idea, 3 vowels. So that may be a way to remember. But you do need to be able to split these ions up. So the other way is also just to look and to see Pb is a metal, Br is a non-metal, Ni is a metal, OH on non-metals. So that's the way you would split. So this would be going to zinc and 2 plus 2 hydroxide when you're writing the equation. So that's 1, and that's the ion. Now, if you're not sure about how to remember the zinc and the silver cation charges, think of a diagonal going up between silver, zinc, and aluminium. So silver always has a +1 charge. Zinc always has a +2 charge when they're an ion. And aluminium, being in group 13, obviously has a +3 charge. So hopefully, I have spent a bit of time here, but I can't sort of stress enough how important it is to know your ions and to be able to break up the compounds in the right place. Just while we over here, and I'll just tidy this up again, is when you're going to be doing the solubility, you have to know your complex ions and effective pH. So if you just have a look at this, thinking of your Zinc, your Zelpo, and your niacin, then you can already start thinking of, okay, if I've get given any nickel compound for my solubility, I must think of complex ions. If I have got silver, because silver comes up both in with cyanide as well as over here with ammonia. So if I've got any silver compounds, I must think of complex ions. And you can see silver comes up a lot. You've also got zinc coming up for complex ions. So remember, zinc comes up over here for complex ions as well as there. And you've got lead. So those were things that have come up in the past. So lead comes up as a complex ion. And of course, copper comes up as a complex ion. Oh, there's another lead. So you can see a lot of these that have come up, they tend to be complex ions. So think of that straight away. And then the other thing that you can think of when you just get given these is, again, for solubility, you not only have to think of complex ions, but you have to think of pH. So if you think of what is an acid is a proton donor, and a base will be a proton acceptor. Now, of course, at level 3, you don't write H+, you write H3O+, always, but we'll just move on from there. So what will react with that? Well, there is a base. So if you change your pH, then both the zinc and nickel hydroxide and copper hydroxide and lead hydroxide and iron hydroxide, if you get given a hydroxide, it will be affected by pH. So that's, again, something you're going to have to discuss when you are asked about a solubility of a substance. Then finally, what else could affect the pH is if any of those anions come from a weak acid. And we will be going over weak acids tonight, but hopefully you already know what weak acids are. So if we look at this, what is a weak acid? We've got this one, because remember, you're expected to know that HF is a weak acid when I had that previous slide up. So that means CaF2 comes from calcium, say hydroxide, plus the weak acid HF. And therefore, if you change the pH, you're going to change the solubility of calcium fluoride. And similarly, this now, of course, this is not one of your expected ones. This is carbonic acid. So they would have to tell you in some way that this is a weak acid. But again, if you change your pH, you're going to be changing your solubility. Then these are all from a strong acid, strong acid, strong acid, strong acid. So those will not be affected by a change in pH. So let me know if there are any questions. But just having that overview helps you work out, because they're going to be coming up in a solubility problem in some way. Okay, let's move on. So the first thing, once we get given our compound, is we normally have to write a solubility equation, as well as followed by a solubility expression. And this is normally an achieved level, just to get you into it. So if, for instance, you were asked to write the solubility expression equation for PbBr2, which was, I think, our first one there. I think it came from last year. So there is our substance. Now remember, you break it up, and there's your Pb2 plus and your 2Br minus. If you're not quite sure how to write the solubility expression, so remember, this is the expression and this is the equation. Sometimes students get confused because they both start with an E, and if they get asked for an expression, they write the equation. So just be clear that the expression is when you use your KS and you do the square brackets and you multiply. So how does this expression work? You simply, once you've written out your equation, you multiply all your products. So if I've got 2Br, it's Pb2 plus concentration multiplied by Br minus concentration multiplied by the second Br minus concentration, which gives us that equation of Pb2 plus and Br minus. Note also the square brackets. Square brackets are used in different places in chemistry, and in this case, square brackets means concentration of. So if I had this in square brackets, I'm talking about the concentration of Pb2 plus. It's quite useful when you're writing explanations and you don't want to write out the concentration of so-and-so decreases. You can just say Pb2 plus decreases, and it just helps save some writing. Right, so here's an example that came up. Again, you would have to write the equation for the equilibrium. So there's always a lot of words that they tend to give. So just focus on write the equation, and you get given an insoluble substance, so you just write the equation. So it's ZnOH, remember brackets 2, and you break it up. Now it is an equilibrium. If you see the word equilibrium, use equilibrium arrows. Don't use a one-way arrow. That will be marked wrong. Okay, so use the equilibrium arrow, and it's Zn2 plus 2OH minus. Now, if you didn't know the charge on OH, again, if you know that trick I showed you about that diagonal for zinc, then zinc is always 2 plus, because we go from 1 plus, 2 plus, 3 plus for aluminium. And if you know the charge on zinc, you should be able to work out the charge on OH. And if I want to now write the expression, it's always Ks is equal to, and then it's the square brackets, and then it's OH minus. Please put in your charges. So you must make sure that everything is perfect. Square brackets and charges. Right, so that's an achieved level, and they tend to always come in. Now we start with the calculations. So with the calculations, I always go, eek! And what I mean by that is always start by writing the equation, because if your equation is correct, it means your expression is correct. And if your expression is correct, you're going to substitute incorrectly, and therefore, hopefully, your equation will be correct. So this is carrying on. As you can see, this is point number 3 in that exam paper. So even if you had done it there, you could rewrite it if you want to, or at least rewrite the expression. Write it out so that you substitute correctly. because I find if students just simply do a mass of numbers and say they transcribe a number incorrectly, it's going to go, you won't get all your marks. Because once you've made a mistake and you haven't shown any working to show how you got to that answer, you can't even get an achieved point. So always at least start with an expression if you had previously given the equation. Otherwise, make sure you write the equation first, then the expression. Then if you're going to be using any shortcut, so like solubility, tell us what your X or Y or S or whatever is. So I'm going to substitute for S. This equation is also given in the resource booklet as Ks is equal to 4s cubed. So you can use that directly, but make sure that you've got the right thing. So what I just do, and I will just drag this up over here, and I'll just clear that. As a trick where students often go wrong is they take they forget about taking the cube root of the 4. So remember, if you want to guess S on itself, by itself, you've got to take 210 times 10 to the minus 6 divided by 4. I always say take that divide by 4 first before you cube it. In fact, write it down so you get this. I don't want to spend too long on this, but so it's 2.1 exponential 6 minus divided by 4, and I like going equal. And that means I know now what I've got to take the cube root of. Sorry about that. It hops off all the time. 5.25 times 10 to the minus 7. And then you take the cube root. So if you've made a silly error with copying something down, at least the examiner can see where you may have made a problem. Now, there should have been a cube root button here. There. So it's 8.067 blah, 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 times 10 to the minus 3. So let's write that down. 0.67. 0.67 times 10 to the minus 3. Now, whenever you do a calculation and you put your final answer down, tell yourself 3 things. Is there a unit? Because not everything has a unit. Ks does not have a unit, but solubility does have a unit. So make sure you then write the unit, because you're not going to get merit or excellence without that. So that's the first thing is you ask, are there units? Next thing is, how many significant figures do I do? Now with pH, I say go to 2 decimal places, because there's always a mess in chemistry about that. But for solubility, you do to 3 decimal places. To 3 significant figures, because your information was given to 3 significant figures. So of course that 7 goes, and the 6 is rounded up to 7. Then your final thing is you say, is this a reasonable answer? And you go, okay, I had 10 to the minus 6 and I'm doing a cube root. So yeah, that looks roundabout correct. Okay. I didn't have an answer like 10 to the minus 13 or something ridiculous where you might have just done the incorrect input. Okay, so you'll always be asked, because it's an achieve level question, this where it's a cube root can go to merit level. But you'll always ask it just to lead you in gently. Then you get asked now the more merit and excellence type questions. And so over here, you get given a lot of information. And again, I find some students get confused by what all these are. So if you don't know the symbol, quantity, and unit, again, spend some time. So volume is measured in liters with the symbol of V. Amount as a symbol of N and is measured in mole. Mass is a symbol of small m and measured in gram. Okay, so here's a little poem you can learn if that helps you. But you must be able to do that, because when I do this, I can go, okay, that's a volume, that's a concentration, and there's my Ks. Okay, so this is the intro, and I am told to assume that concentration of Br minus is insignificant. So remember my EQ method, you always start with the equation, and you go, what equation? Well, what are you given? You are given silver bromide. That is your insoluble substance. So you've got silver bromide going to silver ions plus Br minus, and therefore your expression is based on this. So you've got Ks is equal to Ag plus Br minus. I should always have become a doctor because my handwriting is so terrible. I hope you can read it. Now, once we've got that, we go, okay, I know my Ks. Let's use another color pen. I know my Ks. I have been given a bromide solution over here because I've got a concentration. Okay. And but I have got two volumes. So whenever you've got two volumes and they're being combined, because we're told that it was added to, you know you've got to calculate a new concentration because you've diluted it. If I've got a concentration over here and a concentration over there and I mix them, it means I've diluted it, and so I've got a new concentration. So this is the one I have to calculate because it says there. I really recommend highlighting or underlining the things, putting V's and C's and so on above so you know what it all is. So how can I change my 0.150 that I had originally for my bromide to this new concentration when I've added it together? So what it would just be is, and I'm not going to calculate because I just see the time and it is going quite quickly. I had 0.150, and that was originally in 40 mils. Okay. And, oops, I just want to get the answer here because I had looked it up. Yep. So I had it originally as 40 mils, but when I combined the 25 and 40, I now have 65 mils. So that is my new concentration. Now you might say, well, why did I multiply by 40 and divide by 65? Can't I do it the other way around? Again, just use common sense. If I'm diluting this solution because I'm mixing it to another one, I would expect my concentration to decrease because I'm diluting it. And therefore, to decrease the concentration, the bigger number needs to be at the bottom. And now you just simply solve for silver, and I'm just going to write it down. We know our Ks. If I just substitute in here, our Ks was 5.00 times 10 to the minus 13, and it's going to be 5.42 times 10 to the minus 12. And again, as I say, whenever you do a calculation, you think of what's my unit. I did a concentration. The square brackets means concentration, so it's moles per liter. Second thing is significant figures. I was given 3 significant figures, 3 significant figures, 3 significant figures, 3 significant figures. So I must have my answer to 3 significant figures. And the final thing is this sensible? Well, I've got quite a big number, or quite a small number there, times 10 to the minus 13. This is round about 0.1. So I would expect if this is round about 0.1, then that must be round about 0.000, in other words, 10 to the minus 12 for it to be 10 to the minus 13 over there. So yes, I think by common sense, that looks like a reasonable number to get as an answer. Okay, so very quickly, I'm not going to go here because we're going to be running out of time, but here's another type of thing. So this you can see is a straightforward single ion or single source problem. So the single source here is my ions, so Fe and S only come from FeS. So that's what I mean by single source. So with single source, this is when you can use the Ks is equal to S squared, or Ks is equal to 4S cubed, when both my ions come from one source. Over here, for instance, I couldn't do that. I couldn't use the shortcut because my Ag and my Br came from different sources. So my silver came from this saturated silver bromide solution, whereas my bromide came from my HBr solution. So when you have two different sources, do not use the 4S cubed or the, sorry, there was supposed to be cubed, or 4 or S squared equations, because that's going to be wrong. So always just have a look at the question. So here, for instance, we have now an expression. And is this two sources or one source? In other words, is my H plus and my S2 minus just coming from H2S, or do I have another source? And if you can see, I have a pH of 4.2. So that means I've got H plus coming from elsewhere as well. So I cannot use the shortcut of 4S cubed because my S2 minus does not all come from the same place as the H3O plus does. I've adjusted the pH, so I've either added more H plus or removed some H plus to get to this point. So I cannot use that shortcut, and I've got to do it the long way around. And again, over here, because it says, okay, those are my Fe and S ions, but because it's in this solution with a change in pH, again, I cannot use the S squared equals Ks. I cannot do that because my Fe and my S don't just come from iron sulfide. I've got Fe coming from one solution, and I've got my S coming from my H2S gas that's coming through. Right. I'm actually going to skip that because we've got quite a bit to get through. But here, just to give an overview, remember what I said, when you go through this, work out I've got a volume and link it also to what the solution is, silver nitrate. So that's a concentration of silver nitrate, a volume of silver nitrate, a volume and a concentration, and I've got this Ks. So you can see I've got two different solutions. So I definitely cannot use Ks is equal to 4S cubed. But not only that, I cannot use these concentrations directly because I have mixed two solutions together. So I need to do a different, I have to work out the new concentration by adding my two volumes together. So in other words, the concentration of the silver nitrate would now be 0.105 times 20 divided by 35 plus 20 is 55. And my concentration of my carbonate is going to be 0.221 times 35 over 55. So be aware of that. Also, a trick sorry?
Do we only put in the states for the equilibrium for a saturated solution, e.g. Silver bromide, and equilibrium sign Silver plus aqueous.
Thank you. Yes. Whenever you write equations, then yes, the equilibrium arrow is important and the states are important. So you should always be putting your states in. Is that what was wanted? So for instance,
I think it's do we only put the states in for a saturated solution? So I assume there's other solutions that aren't saturated. Not a chemistry teacher.
Well, you would just be say aqueous, because everything is happening in solution. But if it's a precipitate, so for instance, this is all aqueous and that's all aqueous. But if I was writing my K's expression or equation, then it would be Ag2COR solid, and then it's the equilibrium arrow. And let me just tidy this up. So
it sounds like you do put the states in.
Yeah. Always level 3.
The equilibrium.
Yeah. So when you do strong acids and strong bases, then you only use that arrow as well as for salts. But for this, you will use an equilibrium. Weak acids, weak bases, solubility, you use the equilibrium arrows. So here I would write Ag plus, and I need 2 of them. So you'd write aqueous plus CO3 2 minus aqueous. Yep. Thank you for that. I was rushing a bit. It is an achieved level question. So they may not mark you down on that because they say it's just an achieved level question for that particular part. And for the excellence level questions like this one, they're focusing on whether your calculation is correct. So if you do leave out states, it's not the end of the world. But if you've got time, so if you're not sitting all 3 exams, then yes, try and have it polished, because it just is a very good reflection. They go, oh, the student knows what they're doing. Okay, right. So very quickly, I need 2 lessons on this. Okay, so this is what I said in terms of an excellence question. So, for instance, use equilibrium principles to explain why solubility of zinc hydroxide increases when an excess of dilute sodium hydroxide is added. This is a bit of a trick because it does 2 things. Remember what I said, when you get given a substance, think of, is it affected by pH? And is it affected by complex ions? Or has a common ion been added? So in this case, it's really a common ion has been added because it's hydroxide, which is also pH in this case. And with zinc, remember, you've got that. And we're looking at the OH, so the Zalpo. So we know that's affected. So always use equations. Start off with equations. So what we've got is your original one of your zinc, and I will put in my states to OH minus. Okay, but you have the other equation because hopefully you would have thought of this. And so you know if you add OH minus, then you're going to have your zinc 2 plus your OH minus. Now you would go and look it up in the resource booklet. You would then write ZnOH for 2 minus. Make sure you copy it down correctly, and then you do a balancing to make sure you've got the 4 in front. So that's perfect. Now, with those equations in front of you, it's very easy to say what's happening, because if I add more sodium hydroxide, I am increasing the hydroxide. So by Le Chatelier's principle, if you put a stress into the system by adding the OH, the system will change to relieve that stress. So I am going to move towards the left. The equilibrium position will move towards the left, and I will get more zinc hydroxide being formed when I add some hydroxide. But if I keep on adding hydroxide, so can you see 4 OH is bigger than 2 OH? So if I keep on adding lots of hydroxide, then what's going to happen is this equation, so label them as equation 1 and equation 2. So the examiner knows which one you're referring to. So in equation 2 now, as I'm keep on adding more and more hydroxide, then this equilibrium is going to shift towards the right to try and use up the the hydroxide. So what will happen is once this rim goes to the right, it means I'm decreasing this. If I'm decreasing this, then by Le Chatelier's principle, the stress is I'm decreasing this, so it's going to go more to the right, and therefore more zinc hydroxide is going to dissolve. So can you see by writing your equations first, it's then much easier to see what's going to happen. And always start with your solubility equation. So, or this whole section on solubility, you always start with that, and then you can work from there. The other thing is the common ion. So sometimes if you had chloride and I now add sodium chloride, that's the common ion. Okay, right. So that's the solubility. That's like only 1/3. So here's some other examples. So here you've got something which is again a complex ion. Remember your niacin. Okay. Your other one, Zinc. The Ni. This is for the Zinc N. For if you've got ammonia, nickel gets affected by that, and then the pH. So of course, if you've got hydroxide, OH minus is a base, so it will be affected. Right. Now we get to the acids and bases. And so it's the same thing for solubility. We write equations, we use equilibrium arrows, but now we include the water. And the solubility we didn't, now we do. The reason being is in, like AGBR, all what we're doing is we're just splitting the two ions apart. They aren't reacting with the water. So here, and I think this is what the comment was over here. People write HCl and then they just make it H plus Cl minus. I think that was the comment from the examiner. So this in yellow is what the examiner said for last year's exam paper. So remember, you always make it react with water. So you don't ever have H plus, you have H3O plus. We want to see that hydronium ion. So here's your weak acid. You have it with water. And whenever you've got an acid, you must land up with a hydronium ion on the right-hand side. If you've got a base, you must land up with an OH minus. If you don't, you haven't written the base hydrolysis or the acid hydrolysis equation. You've gone wrong somewhere. So here, for instance, ammonia, if I react ammonia with water, then, sorry, I haven't put in my states. You should put in your states. Again, going to have that plus OH minus. If I landed up with H3O plus here, I've made a mistake. Right. Now, why are these hydrolysis equations important? Because you will be asked a question on the relative order of species in solution. So when do we use a straight arrow and when do we use an equilibrium arrow? When we have a strong acid or strong base or a salt. So those arrows are normal arrows going all the way to the right, because by definition, these will dissociate completely. But notice I have put water there. This is an ionic substance. Remember, HCl is actually a molecule, whereas this is not a molecule. It's an ionic substance because it's got a metal with a non-metal. And therefore, you'll notice I haven't put water in there. So in case you're wondering why water wasn't there, because this is ionic. This is, again, an ionic substance because I've got a metal with a non-metal. So you'll notice I don't have water in there either. You only add the water for molecular substances. The only exception when you try and use that metal, non-metal route is, please remember, there's one exception of ammonium. So if I had, for instance, ammonium chloride and I was writing this dissociation, I wouldn't write water either. I would just simply write NH4 and say, okay, that's the cation, that's the anion, it is ionic, and I'll just make it go to NH4 plus Cl minus. Okay, and put in your states. Okay, so here, if it's weak, you must land up with your hydronium ion if it's an acid, and you must land up with your OH minus if it's a base, and you must include your water, and it must be an equilibrium arrow. Then finally, what I've got here is when you do the relative order, you've always got water. Water will also always dissociate, but Kw is very, very small, so it hardly dissociates. So you should, when you're doing your explanation, you should refer to the Ka given. Like you can see, there is not very much dissociation at all, but a lot more dissociation, say, of this weak acid, because this is run about 10 to the minus 5 for this one. There'll be a lot more dissociation of ethanoic acid than for water, because water is only 10 to the minus 14, so there's much less. And therefore, there will be a lot less OH minus, for example. So here is, for instance, an example. So when you get given a salt, and I recognize this as a salt because I've got a metal and a non-metal, so the first thing you do is you write your straight arrow because it's a salt and I haven't added water, okay, because it's just a straightforward. And now you go, oh, one of the things I have to know, remember how I started off? These are the strong acids, strong bases, weak bases. This is a weak base you need to know. So you know that this is a weak base, so it will react with water. Please put in states, and now it's an equilibrium arrow. OH, because it's a weak base, so I must land up with OH minus. So always have that in your head as you check, is my answer sensible? Whoops, let's keep to that, OH minus. Right, so when I want to do the species, I remember I must do H2O, splitting up to H3O plus OH minus. So when I want to do my species, by my arrow, all of that is gone. So I don't have any sodium ethanoate in my solution. It's gone. Okay, it's all gone over. Now I have equal amounts of this and this. So you would say when you were listing all the species, you'd have ethanoate, which is a similar concentration to your sodium concentration. A tiny bit, okay, like 1/10,000th of that ethanoate is going to react with water to form equal amounts of ethanoic acid and hydroxide. So these will be in a lot smaller concentration than the ones on top, but will be present in equal amounts. And then because of water and Kw being really, really, really small, I will have some hydronium ion. I don't have to really talk about the hydroxide because I've mentioned the hydroxide there. And yes, it means that the hydroxide is slightly more than but we're going about like 1/10,000th or what's 10 to the minus 14, like millionth. It's tiny. It just doesn't really affect that concentration. But we do have to say that there is some hydroxide present. Okay, right. So that is a guaranteed question, and it's guaranteed for an excellence level. And related to that is also then your properties, because you have to then explain why these have change in pH or in conductivity. So those are normally the things that they ask, is conductivity and pH. So you know that they're all the same concentration because they're all 1 mole per liter. So now you have to look at it, and this is where your knowledge of the strong acids and strong bases, weak acids, weak bases come in. So this is, I'll just change my color here. That is a strong acid. So if I had 1 mole per liter, my pH over here is 0 because 10 to the minus 1 is 0. Okay, remember your pH is equal to your negative log of your H3O plus. So you could even say what it is. This is, hopefully you will know, a weak base. Okay, that's a strong acid. And this is a salt. So the salt is from a strong acid and a weak base. So it's a salt from a strong acid, weak base. So if we were doing it in order of pH, this would be the lowest because it's a strong acid. So this is number 1. This, because it's from a strong acid, weak base, is going to be more acidic than a weak base. So this is going to be next highest in pH, and the base will have a pH of over 7. So this is going to have the highest pH. So this will have a pH of 0. This will have a pH of round about 3 or 4, and that's going to have a pH of round about 8. I mean, you won't be expected to know that, although you could work out the HCl. But you should be able to recognize from those lists that have to know what they are. And then from the conductivity, always say how you know. For instance, explain what pH is. pH is the hydronium ion concentration. So conductivity, you have to explain in terms of it's the movement of charge. So it's a solution that allows a movement of charge. And the more charge, the greater the current can be. Okay, so now you've got to look at the degree of dissociation. So for both of them, you have to, for both pH, because a strong acid dissociates completely, and that's how we know we've got lots of hydronium ions present. But it also means we've got lots of so it's H3O plus Cl minus. We've got lots of ions present. So for every 1 mole, we've got actually 2 moles of charges. For the other ones, because this is a weak base, this is going to be mainly methylamine and not very much at all. So always remember, always add your water, and it's going to be CH3NH3 plus OH minus. Remember, a base must have OH minus. And then the last one, which is CH3NH3Cl. Now, it's a salt. Again, the metal, non-metal doesn't really hold very well over here. This is the same as the ammonium. So that's actually the cation. And you can see that because it's got a 3 there compared to the 2 there. So you know that the nitrogen has got an extra hydrogen. So when that dissociates completely, because it's a salt, can you see it's very conductive because I've also got 2 moles per liter of charges, just like the strong acid. So you would have to explain that. Any questions? I am starting to rush. I do realize that because there's actually quite a bit more to go through. So just pop questions in if you're lost and you want me to go over something. So here's another way they can ask you that sort of equation. So instead of just giving you 2 or 3 things and saying, compare their conductivity or so on, they can actually give it to you in terms of your Ka or pKa, because the size of the pKa will tell you how much it dissociates. So a strong acid has got such an enormous Ka that we just ignore it, and so we only give it for weak acids. But can you see that this has got a smaller pKa than that. So remember, the lower the pH, the more acidic. So the smaller the pKa, the more dissociation. So this will have the lower pH than that, because this will dissociate more into its acid, whereas this does not dissociate as much. So if you were writing this out, remember, always write equations. Even if they don't ask for equations, write equations, because they really help you keep on track of what you need to explain. And as I say, please put in states compared to your other one, which is NH4 plus H2O. So even here, by writing the equation, I think you can recognize you've got a base there. So you're definitely not going to have a high, as low a pH as you would have for the acid. So this is a weak acid, that is a weak acid. It's just this one's a heck of a lot more weaker than that one. Okay, Andrew, just checking. Do I stop at 8 o'clock exactly?
Give or take. I mean, if you want to go for a few more minutes, just to close up the question.
So I'll just go very, very quickly now, because it's really the same thing over again. So I'm just going to be putting some clues in. You're often asked you're given some arbitrary compound, and then you've got to write an expression. So always write the equation first, and you must, in your Ka expression, you must have, now I did just copy this off the internet, so it's just a H plus instead of H3O plus. But if you don't have an H3O plus in the numerator, you have not got a Ka expression. The same thing for a Kb, you must have an OH minus. So a lot of students, when they get given this, for instance, they don't see it as a salt. And then they'll write, okay, Ka is equal to, and then they'll write CH3COO minus Na plus all over CH3COO Na. Now, does that make sense? Is that a Ka expression? Does it have an H3O plus in it? It doesn't, so you know you've done the wrong thing. You should have split it up first and then done the next equation. Now, there's a whole lot of pH equations, but if you follow this EQ thing, write the equation, then the expression, and then substitute, you shouldn't have a problem. You should also write your assumptions. It's just a good look, and it's better for excellence level to do that. So in the last minute or so, you will be given a titration curve. So you could either have to draw part of it, or perhaps put in some units or something like that, but you will be given something like this. So these were for the last 6 years, the sort of things that were given. Now, you can see whether it's a strong acid, strong base, or weak acid, strong base sort of thing, because of where it starts. If your pH starts below 12 or ends below 12, then you know you've got a weak base in there somewhere. Similarly, if you start at round about somewhere between pH 2 and 4, or you end at around about pH of 12, then you've got a weak acid. Okay. Notice also both the weak acid and weak base, they have that, they don't go straight. So can you see that goes straight over, whereas the ones with the weak, and even over there, you can see there's a bit of a glitch down. I mean, I've exaggerated it there. That's another way you can see whether it's weak. So I can immediately, by looking at it, go, that's weak. Okay. I don't even have to look at the pH. I can see it's a weak. So I know this is a weak base. And you can never have a weak base, weak acid titration. It'll be a total mess. So if you got a weak acid, you know you've got to titrate it with a strong base, as you can see here. And if you've got a weak base, you are going to definitely titrate it with a strong acid. So those are sort of helpful points. Other helpful points are halfway to the equivalence point, which is halfway up the steep part of the graph. This is the pKa. Well, sorry, it's over there because that's the pH. So that value over there, whatever that pH is, that's the pKa of that weak acid you're working at, because sometimes they ask you to work it out and you can get it from the graph. Right, we are at 8. So there are quite a few things, but we'll just leave it at there. Those are sort of helpful tips. One final thing is, okay, with the suitable indicator, most students got this correct. Just make sure, that your equivalence point is within the pKa of the indicator, not of the acid, but of the indicator. So here I've got my equivalence point at around about 6. So actually none of these, this doesn't match that one, but none of these would actually be suitable indicators because they're not within one pH unit of a pH of around about 6. I should have it between 7 and 8. I could, at a push, use Cresol Red, but it's not very good. Yep, you're going to be using titration calculations. One final thing in terms of buffer, I like using the Henderson-Hasselbalch equation, and a lot of students, because this is not given, actually I'm pretty sure it's not given. Can I just quickly check in the resource booklet right on the top? Yep, you can see it is not given in one of the equations. So if you want to remember it, because a lot of students get confused. So remember, it is a plus there. It's always pH, and then it's a pKa of the acid, and it's a plus. So that doesn't will stay like that. And then one way is think of A is the first letter in the alphabet, so it's at the top, and HA is at the bottom. So the base is always at the top. I know B starts with A minus is the conjugate base of HA, so that's how it works. Or if you've got the weak acid at the bottom, think of HA as being heavier. So if you do tend to think of this as base and you think of B, then just think of HA as heavier, so it's always going to be at the bottom. So you put in the concentration of the acid at the bottom, and then it's a straightforward calculation. Sorry, that I did miss quite a few concepts at the end, but hopefully I did help cater for some of the weaker students and some for the high-flyer excellent students. Were there any questions, Andrew?
No, it looks like you've pretty much just about covered things. We'll just if you have your questions, chuck them in the chat now. Otherwise, we'll close things off. Just like to thank you, Deline, for taking your time to hopefully get some students over the line. Yeah.
I can fill this in a little bit more detail. And do we upload the documents anywhere that sort of from the YouTube thing?
Yes. So
yep.
The what do you call it? The Word document that you're working through, we'll try and put it in the description when the video gets uploaded.
Yeah, I'll convert it to a PDF, so there's no issues with the, how some students, if you're in Pages, the Word document might be a problem. So it'll be a PDF. And I highly recommend, if you find an area you are struggling with, so like say it's titration calculations or solubility, if you go to No Brain Too Small, that has got an excellent site where they you can do all the questions since 2004 on that sort of concept. And they have all the questions from all those exam papers plus the answers. So you can practice, one titration calculation, one after the other, after the other, after the other, until you've got it perfect. Because you don't have to revise the stuff you only have to revise the stuff that you are having problems with.